Okay, well, I'm happy to welcome everyone to the last talk of today and to announce our speaker, Kristin Lauter. And the title of her talk is Curves over Finite Fields and Applications to Cryptography.
So thank you very much, Alice. Can everyone see my slides in full screen mode? Okay, good. Thank you. So I'd like to start by thanking the organizers. Thank you so much for organizing this conference. I know with COVID and everything that everyone is facing, there's been a lot of challenges and it takes a lot of work to organize these conferences. And I really appreciate that. And thank you for the invitation to speak. But in particular, also thank you for producing together with many other contributors the beautiful book, which is the book based on Sayre's Harvard notes from 1985. So that means a lot to me. And given the topic of this conference, celebrating the publication of this book and these notes, I thought I would take the liberty to talk a little bit about my experience with these notes and the impact they had on my career, and in particular, how this led me fairly naturally into working on cryptography and curves over finite fields in cryptography. So Sayre's course in 1985 covered a lot of ground, focused on rational points on curves over finite fields. And the notes that were the handwritten notes that were taken by Fernando Gouveia were circulated. I had a photocopy of them, which I carried around basically throughout graduate school. And that, along with my copy of Sayre's Local Fields, were my prized possession. That was the only thing that I really did not want to lose, were those two things. They were dog-eared and marked up in every possible page, and they were really like my best friends. And the photocopied notes, I had them bound with a purple cover, and anyone who knows me knows that purple is my favorite color. And so they were really my good friend. But that was, essentially between 25 and 30 years ago now. So I don't remember everything that I was thinking about then. But preparing this talk was a really nice opportunity to think back about those notes and the topics that Sayre covered. So one of the main topics, I don't remember if it was part 1 or part 2 of the notes, but was constructing curves with many points. So constructing curves over finite fields for lots of different genus G and lots of different fields FQ that have many points. So one of the major tools that he introduced, as far as I know, I don't know any other place before that where this was proposed or used, was that he proposed to use class field theory to construct curves with many points. So the idea there is that instead of thinking of a curve as being given by an equation, some geometric object, or thinking of it as a scheme, instead he thought of it as a function field. And to construct curves with many points, the idea was to construct extensions of function fields. So you could start with some base base function field, even, for example, just the projective line, and then construct extensions where, well, what he did was he controlled the ramification in the extension, and that determined the genus. And then he controlled the splitting behavior in the extension, and that's how he was able to get a lot of points. So this turned out to be a very, very fertile ground for ongoing work, which I'll mention more in a minute. And that was really kind of the first aspect of his notes that I personally focused on. And that was actually a topic that was suggested to me by Renee Self. So I really appreciate Renee's role in getting me into this field by connecting me with these notes and suggesting various problems. And working on the class field theory constructions of curve with many points was one of those directions that Renee suggested initially. So another aspect of Sarah's work in that course was to look at various known families of curves given by equations that had many automorphisms and many points, including, for example, the Suzuki and the recurves, which are the dimension 1 examples of Deligne-Lustig varieties in characteristic 2 and 3 that have a maximal number of points. And then another aspect of the work that he did there was to look at actually making tables for just for the field F2. So when Q equals 2, tables of N2 of G for small genus, for genus basically 1 up to 20. So he had an interest in figuring out, like, F2, that seems small enough. You know, shouldn't we be able to know what is the maximum number of points possible for genus G for a small g? And I know a lot, there've already been quite a few talks in the conference, so I'm assuming that this notation has already been introduced, but NQ of G is the notation that he introduced for the maximum possible number of points on a curve of genus G over the field FQ. So what I did was you can see actually in my background, a kind of a snapshot of the tables, and this is for Q equals 2. So this is a snapshot from today of the many points tables, which are available online, put together and maintained by van der Geer and Howe and myself, along with Christoph Ritzenthaler. And if you look at the snapshot that I have actually on my background here behind me and also on the slide, you can see that for Q equals 2 and genus 1 to 20, it turned out to be not such a simple problem to figure out the maximum number of points. Because if you look at this table, you can see that even today, roughly 35 years later, there are still gaps, there are still unknowns. So I apologize if there's people that have written papers solving these gaps and they're not in the tables yet. But from what I can see, you still have a few gaps. So what do I mean here? If you look at the right-hand column in the bottom, you'll see that if there's a single number there, like, so for Q is fixed in this table. So Q is 2, we're talking about curves over F2. And so for genus 1, there's an elliptic curve with 5 points, and that's the maximum. So there's a single entry there. So everywhere that you see a single entry, that means that there is a curve known to exist that has that number of points and that actually matches the best upper bound that we know of for the number of points that a curve can have of that genus over F2. So, but if you go down to genus 12 here, you'll see that there's 2 numbers. So that means that, yes, there's a curve known that has 14 points, but the bound is 15, and it's not known whether there can be a curve with 15 points. And you might ask, oh, these things seem pretty small. How come we don't know that? Well, it's just that we don't have a way of, like a systematic way that's computationally feasible to just run through, all possible genus 12 curves and figure out whether one can have 15 points. Let's move on to another part of Sayre's notes. Another aspect of the problem that he studied was actually, imping the upper bounds on the number of rational points. So you could already see that in the table. I'll mention that again in just a minute. But I mean, when I was in graduate school, at least in the US, there weren't that many people working on curves over finite fields in mathematics. And those that, the mathematicians that I knew, for example, at University of Chicago, didn't know that much about the field. And so if I mentioned that I was working on, improving upper bounds on the number of rational points, they would just say, oh, well, what is there to do? There's the Weil bound. Everybody knows there's the Weil bound. So it wasn't really all that popular of an area of research, let's just say, at that time, at least not in the US. And so the first improvement that I know, and for example, I know Everett covered this in his talk as well, the Sayre bound, Sayre introduced an improvement so that instead of just q plus 1 plus 2 square root q times g, 2g square root of q as the kind of the error term for the number of points, you actually have this greatest integer part inside the 2 square root q. So if throughout this talk, little m will be the greatest integer part of 2 square root q, and the Sayre bound is just q plus 1 plus g times m. And then there's a word which came to be one of my favorite words for many years, which was defect. And defect, what means that's the distance that you are from the Sayre bound. So if you have defect 0, that means you're a curve which is meeting the Sayre bound. And if you have defect 1, then you're 1 less than the Sayre bound, et cetera, et cetera. So I'll just go back to this table just to point out something kind of interesting and fun. If not in my slides, but in the online version of the table, if you go to this website, if you hover over this number, like the number 5, 6, 7, 8 here, it will tell you the defect, which is very nice. And so for those people that thought that the Weil bound or the Sayre bound, which coincide when Q is an even power of a prime, by the way, but for those people that thought that the Weil bound was the end of the story, you might be interested to hover over the defect as you go down this column. And what you will find is that the defect increases from 0 to about 20, essentially 1 by 1, each line that you go down. So the defect is from the Sayre bound is not at all 0. It's like 1, 2, 3, 4, 5. So, you know, for genus 11, it's like defect 11. It just goes down. So it's kind of a very interesting phenomenon there. And you might conjecture something there, but we also know a lot more now about what happens for much larger genus. So those patterns that you see on the very small genus, you know, don't necessarily continue as they look like they might in that table. So in particular, another really important thing that Sayre included in his course and in his Harvard notes were the explicit formula to improve the Sayre-Weil bound in higher genus. So if you just think about the Sayre bound as being a line, it has, you know, intercept q plus 1, but as it goes, you know, it has slope equal to m as the genus gets larger. And if you're not familiar with Oesterle's explicit formula method, which Sayre presented in his course and which is now written as a chapter of the book, you could just think of it as if Q is fixed and you're making a graph, and as you go to the right, the genus is increasing. I'm sorry, I'm not mirroring, so my hand might be heading in the wrong direction when you're looking at me, but I wanted you to be able to see the tables in my background. So as the genus increases, instead of just having a line which is of slope m, the explicit formula give you lines which are kind of smaller and smaller slope. And so it kind of looks like like a convex envelope, which is not just a line heading to infinity with a single slope. So from that, you can see that you're essentially getting further and further away from the Weil bound as the genus gets larger. So another very important technique that Sayre introduced was the idea that if you want to fix the number of points on that you'd like to have on a curve of genus G over a field FQ, that you can actually, in principle, make a list of all the possible zeta functions that can occur. Now, the zeta function, I apologize, I didn't write whole slides about zeta functions. I'm not sure if that was covered extensively in other talks, but the zeta function encodes the number of points on the curve over the field FQ where it's defined and over every extension of FQ. And so there's a lot of restrictions on the zeta function. It's not just a random polynomial because, for example, you can't have fewer points on the curve over an extension field of FQ than you have over FQ. You can't have a negative number of points on a curve over the extension field that of FQ when it's defined over FQ, et cetera, et cetera. So there's a lot of conditions like this that were useful, and they were used in both Oesterle's method and in the Sayre's approach to making a list of possible zeta functions. So right in the beginning of the book, you'll see the list of possible zeta functions for defects like 0, 1, and 2, I think. So finally, another thing that Sayre covered, and this is not an exhaustive list of what's covered in the book, of course. This is just aspects of the book that were particularly meaningful to me, where I worked on them and did follow-up work. So another aspect of his book was to actually determine, his notes, I'm sorry, was to determine NQ of 1 and NQ of 2. That is, if you look at just genus 1 or genus 2, and then any finite field FQ. So for example, for genus 2, I believe I got this citation right. I looked it up. It's theorem 3.2.3 in the book. So, but in order to do this, he introduced a surprising number of techniques, including the gluing technique, which I've used throughout my career for many, many different things. So Sayre's gluing technique, and again, I don't know if there's a reference that predates Sayre's work for this type of gluing, although it certainly uses, a lot of what was known about, abelian varieties, and according to Mumford and others. So the gluing technique to create, for example, a genus 2 curve, you start with 2 elliptic curves, and you look at the torsion, like the end torsion on the elliptic curves. So like E1 bracket N and E2 bracket N. And what you need is to glue them, you need a map, which is a bijection of the end torsion, but which is also if I remember correctly, an anti-isometry with respect to the Weil pairing on this torsion. And if you can find such a map, then you can glue these elliptic curves together by looking at the graph of this map and quotienting the product of the end torsion, the end torsion on the elliptic curve 1 cross the end torsion on the elliptic curve 2, and quotienting it by this graph. And then with a lot of beautiful mathematics in the background, you'll actually end up with a genus 2 curve. Now, this technique, as you could probably see, involves the Weil pairing. And in fact, it led to him to be interested in the study of the existence of certain Hermitian modules, which need to exist in order to have these types of gluings. And so in order to determine NQ of 2, just for genus 2, he was led into all these, other interesting areas of mathematics. And it was nice to see that we're having, a talk on Hermitian modules in this conference as well. So another thing that it actually involves, somewhat surprisingly to me when I first saw it, is studying solutions to certain Diophantine equations. And that's because if you go back to my slide where I defined M here, you can see M being the greatest integer part of 2 square root of Q is a somewhat unnatural, number theoretic concept. But it turns out that if you're expressing a power of a prime, so let's say Q is P to the E, then it really matters kind of how far that is from its own square root. So you end up expressing primes and powers of primes in terms of things that turn out to be Diophantine equations that you want to solve. And according to whether you have a solution to those equations or not, and using, for example, I forgot whether it's called the Skoll-Noether theorem, you can figure out when there's like no solutions to such equations, things like that. That's what was required in order to be able to completely classify, what the maximum possible number of points for NQ of 2 would be. So I'd like to very briefly talk about, how all of this work kind of affected my own career. So thanks to Rene Scoff and his notes from a course that he gave shortly after Sayre's 85 course, I started working on using class field theory to construct curves with many points, and essentially focused on that in my PhD thesis, including constructing record curves and also families of curves, and follow-up work, including formulas for the number of points that you could attain using these methods, and also characterizing the Suzuki and recurves, those families, in terms of covers via the class field theory construction. It also led me to a great collaboration when I was a postdoc at Max Planck with Kerem Belabas, where Kerem wrote extensive Paris code for constructing curves with many points using the class field theory approach. And that was my opportunity to learn to use Paris, which has served me throughout my career. So that was a very nice collaboration, never published, unfortunately. And then there was a whole series of work, Roland Auer, but also focusing on Drinfeld modules, Niederreiter and Zing and others who were working on a kind of a related construction, basically like a non-abelian analog of the class field theory constructions. And that is covered to a large extent in a book by Niederreiter and Zing, in fact. So for me, one of the important transitions was actually when I was a postdoc. I think, again, it was Rene Scoff that suggested that I work on seeing if I could improve the upper bounds anymore by looking at Sayre's technique of where he had determined the possible zeta functions for small defects. And so, in fact, looking at that, I came up with a general algorithm for determining all possible zeta functions for a given NQ of G, which was published in the proceedings of the AMS. And the nice thing is that that led me to a kind of very long-term collaboration with Everett Howe to continue to improve the upper bounds, so improving Sayre's bounds for the number of points, especially in small genus, where we could make, even for rather large defect, not just defect 0, 1, and 2, but for lots of different defects, you can see actually reflected in the tables, the fact that the code that Everett wrote to be able to compute these zeta functions is now widely used. And so finally, kind of a culmination of all of this work for me was a collaboration that was inspired by a letter that Sayre sent me about the Torelli theorem, and which was published as an appendix to my paper in Compositio in 2002. I was able to determine, not exactly determine NQ of 3, but to determine that the defect, that's why I have a star here. NQ of 3 is, as far as I know, still not known, but NQ of 3 was able to show that the defect from either the upper, lower, or lower bound is always bounded by 3 for every Q. And again, that involved a kind of a study of the Hermitian modules technique that Sayre had introduced, and gluing techniques and solutions to certain Diophantine equations, which were a generalization of what Sayre had done to handle the case of genus 2. So at this point, you might ask, what does all of this have to do with cryptography? So the nice thing is that there are a lot of really beautiful and fundamental, constructions from this area of number theory, which is basically kind of an intersection of number theory with algebraic geometry, curves over finite fields, which are very, very important for cryptography. So the connections might seem a little bit spurious, but I'm trying to kind of explain my own progression as well here. That zeta functions are actually very important in cryptography in the following sense. So I'm going to talk a little bit more about elliptic curve cryptography and genus 2 cryptography, which are based on the discrete logarithm problem. So throughout, I'll use these abbreviations that I've written down below on the slide. DLP is the discrete logarithm problem. DH is Diffie-Hellman, which is for key exchange, and DSA is for digital signatures. And the problem is that there isn't a direct correspondence application of Sayre's techniques to cryptography, because in cryptography, you're not necessarily interested in using a maximal curve the way that you might want to use in coding theory. For coding theory, it was very important to have as many points as possible for the algebraic geometric constructions of error correcting codes. But in cryptography, it's not exactly that. The restrictions are more along the lines, the main thing that you really want to have in cryptography is you want to have a prime group order if possible, or a very small cofactor if absolutely necessary. And so in fact, what you're led to is wanting to construct elliptic curves over very, very large cryptographic size prime fields. So this is, large field, small genus instead of small field, large genus, as we were discussing in the previous slides. But what you need is to be able to actually construct a curve with a given number of points, rather than another approach is, of course, that you randomly select curves and then count points on them until you find one that has a suitable prime order. So just to give you kind of a little bit of an overview for the rest of my talk and the things that I'm going to cover, let me hit some of the other connections that I see between Sayre's notes and cryptography. So another very important tool in cryptography is the Weil pairing on an elliptic curve, or all kinds of variants and extensions. So the Tate pairing, or the eta pairing, or the R eta pairing, all these kind of variants that were introduced to make evaluation of the pairing more efficient. But the basic underlying idea comes from the Weil pairing on an elliptic curve, and the Weil and Tate pairings, and also their generalization to higher genus Jacobians. And in fact, this is important in cryptography, both for attacking and existing systems and for creating new ones. So I'll get into that a little bit later. And then the final connection also connects a little bit back to Everett's talk on isogenies and isogeny classes, and that is the relatively more recent proposal to use supersingular isogeny graphs in cryptography, dating back to 2005 in my joint paper with Dennis Charles and Eyal Goren. So let's focus on elliptic curves in cryptography for a moment. So cryptographers mostly, especially if you're not working in characteristic 2 or 3, will use the short Weierstrass form of an elliptic curve, which is just given by this easy equation, y squared equals x cubed plus ax plus b, where a and b are elements of some large prime field. Now, at the time when I started working in elliptic curve cryptography, the minimum bit size that you would want to use for such a prime was about 256 bits. And this has actually recently been increased to the recommendations currently suggest using 384-bit primes at least, most likely due to the advent of the potentially imminent existence of a quantum computer. So elliptic curves are a beautiful object in mathematics because they're both a curve and a group. So you have an identity in the group, which is the point at infinity, and a group law, which is constructed via the infamous chord and tangent method, where you pass a line. If you want to add 2 points, Q1 and Q2, you pass a line through them and you look for the third point of intersection with the elliptic curve, and then those lines, those points on that line should be, they're the divisor of this line, so they should essentially be 0 in the divisor class group of the curve. And so Q1 plus Q2 should be minus R1. So that's where the group law on the elliptic curve comes from. And so fairly early on, I got interested and involved in whether it was worthwhile to do cryptography also on the Jacobian of genus 2 curves, not just elliptic curves. So Koblitz had suggested using the Jacobians of hyperelliptic curves in cryptography. And so you can see kind of the analogy, how it's analogous with the elliptic curve case. So now let's take a model for genus 2 hyperelliptic curve, y squared equals f of x, where f has degree either 5 or 6. And now, unfortunately, the chord and tangent method is not going to work because it's either a quintic or a sextic polynomial here, f of x. And so if you just take a line and pass it through 2 points, you won't just get one other point of an intersection. So instead, what you get is you can think of the group associated to a genus 2 hyperelliptic curve as being given, its elements are pairs of points on the hyperelliptic curve. And in fact, what is often used for efficient manipulation of these elements is the Mumford representation for, and this is actually more general than genus 2, Mumford's representation for the elements of the Jacobian of a hyperelliptic curve is actually given as just a triple of polynomials, a of x, b of x, c of x. And it's a very nice representation because the roots of a of x are just the x coordinates of the points that are in the, so if it's genus G, then there's going to be G points. And then b of x actually is a polynomial that goes through the kind of the y coordinate of those points, meaning that it picks out, because hyperelliptic curves, you could have either plus or minus the y coordinate. So it picks out whether it's the positive or the negative. And then c of x is just the kind of the cofactor that you get with a of x in order to make b of x divide, I think it's f minus a times c, if I remember correctly. So the nice thing to notice there is that there's a group law, and I'm not sure whether, I guess Cantor's algorithm, if I remember the story right, was kind of a write-up of a discussion of René Scoof and Hendrik Lenstra. Somebody will probably have to correct me on the history there. But the idea is that it's very analogous to the Gauss's composition law for quadratic forms in an imaginary quadratic field. And so Cantor's algorithm for operating for the group law really on the Jacobian is what you get if you apply kind of the idea of Gauss's composition law from the quadratic imaginary fields, if you apply that idea to function fields now. And so one of the things that I got interested in was in my exploration of this topic was the kind of the geometric analog of Cantor's group law. So Cantor's law just kind of operates on this triple of polynomials, this basically the same way that Gauss's composition law operates on a triple corresponding to a binary quadratic form associated to an imaginary quadratic field. But so there's also a geometric group law for genus 2 Jacobians. You can see it, for example, in the book of Castles and Flynn. And so one of the things that I did was to write down a proof in a paper in 2003 in a volume in honor of Ruth Mishler, actually, showing that Cantor's group law for genus 2 was actually the same as the geometric group law for genus 2 Jacobians. A good thing, because we wouldn't want to have two different group laws floating around. And ever since then, you see kind of this obligatory picture in almost every talk by cryptographers on genus 2 cryptography. And since it's my favorite picture, I actually had it on my office wall, on my office door for many years. And of course, that's why I put it in purple too. But there's a little bit of a funny story with regard to this picture, kind of exciting. So just a couple of weeks ago, I was actually interviewed for a documentary by Werner Herzog on brain-computer interfaces. So he's making a documentary. And because of my work on privacy for brain-computer interfaces, emerging devices, I was interviewed for this documentary. And to my surprise, after 45 minutes of filming and questioning, his wife, Lena Herzog, who's a famous photographer, came and handed me a blank sheet of paper and a marker and said, please draw your favorite mathematical equation. And so guess what? I drew this picture and the group law and wrote down essentially what you see on this slide here, which is a very, very old slide of mine. And so she wanted to do the still life photography for the documentary. So she photographed me using this picture. So you may see it showing up in a documentary by Werner Herzog in the near future. So sorry for that little diversion there. So moving on, you might say, why genus 2? Elliptic curves were, very well known, highly optimized, standardized, in fact, and even deployed worldwide in all kinds of systems. So why even think about genus 2 cryptography? Well, first of all, from the mathematical point of view, it's a natural extension. They're beautiful objects, and they also lead to lots of interesting and beautiful mathematical questions. In particular, if you think of using the Jacobian of a genus 2 curve in cryptography, again, you're going to need a large prime order group. So now you're left with the question of constructing genus 2 curves whose Jacobian has prime order. And although the prime field would be FP, the size of the group would actually be FP squared. So that gives you an advantage, because now in order to get a group of size like 256 bits, which is what you need for cryptography, you only have to start with a field of size 128 bits. And when you have to implement, field arithmetic on a computer, you have to break it up into chunks which fit in the word size of the computer. So at that time, when I was working on this, the word size was typically 32 and then 64, but 128 is certainly a convenient word size to work with, although I'm not sure how many of our computers today are actually using 128-bit word size, but certainly 64. So in fact, that leads you to a lot of really interesting research, which I certainly focused on for a number of years once I went to Microsoft. And that is, how do you construct curves with a given number of points, both elliptic curves and genus 2 curves, and then beyond that for higher genus and genus 3 in particular. So another reason that you might want to use the CM method instead of, which relies on zeta functions, instead of using point counting, is that for constructing curves, safe curves which are twist secure, you also want to control the number of points on the twist of the curve. So if the curve has p plus 1 plus t points or minus t points, then you also want to make sure that the number of points on the that the opposite, like the twist, would also be kind of twist secure, so isn't for example, doesn't have smooth order. And what is the CM method? Just at a very high level, I don't have time. I used to give whole talks about the CM method, and I don't have time here, but it basically looks at the Frobenius that you would need in order to get the prime order that you're looking for. So you fix n equal to p plus 1 minus t, and then you compute d equals t squared minus 4p, and Frobenius will lie in this field, imaginary quadratic field, q square root of d. So then the problem is that T is generically going to be around the size of square root of P. So T squared is roughly of size P. So now if P is 256 bits, you're left with a D, which is, 256 bits, which is a huge monster. And these Hilbert class polynomials have coefficients which are exponential in D. And so that's not good. So I do see, so happy to see Drew Sutherland here at my talk. And Drew did a tremendous amount of amazing work on being able to compute these Hilbert class polynomials using what we called the explicit Chinese remainder method, and was able to push to fairly large D that could be used, and created tables that can now be used for constructing elliptic curves with prime order. So because I don't have a lot of time, I'm going to skip over the kind of analog of the CM method for genus 2, which was one of my favorite topics for many years. But there you need to actually, instead of just computing the Hilbert class polynomial, you need to compute 3 Igusa class polynomials, which can be potentially extremely large, even for very, very, very small quartic CM fields. And so the red lines in the bottom, those 3 red lines, this is one of the earlier examples that I computed. That's just the denominator of these polynomials, which is pretty horrendous to have to recognize. And then in the top line here, you see the factorization of that denominator. So you could see that it was very, very small primes that actually appeared. And so that led into a whole interesting area of work to study what are the primes of bad reduction of these genus 2 curves, which are exactly the primes that appear there in the denominators of these Igusa class polynomials. And so I just wanted to say one more thing about genus 2 and one more thing about genus 3. And for my talk for tomorrow, we'll cover a little bit more about the future for genus 1, 2, and 3 curves. And that is that in 2013, we showed in a Eurocrypt paper with my collaborators for the first time that you could actually get faster group operations on genus 2 than on elliptic curves, genus 1, for the same security level. So the first line was here, which is in red, is genus 1. It's the NIST prime curve, and the second line is in green. It's a generic genus 2 curve over a field of 127 bits. So there's other, I'm not going to go into all the other lines on this table now. I'd be happy to answer questions about them. And again, this work is dated, it's from 2013, but it showed for the first time that the actually 248,000 cycles for the genus 2 operation versus 658,000 for the genus 1. I'd also just like to mention, I think there will be more talks about this, at least if not this week, then next week at AGCT, hopefully. Ongoing work on genus 3 by many people, including some of my wine groups, my wine 1 and wine 2 group. Many of the people listed here on this slide. Okay, so since I only have 1 or 2 minutes, I think I'm just going to briefly conclude by mentioning the use of the Vey pairing in cryptography. So the first kind of appearance was as a negative tool that is used to attack, for example, supersingular elliptic curves via the MOV attack, the Menezes-Okamoto-Vanstone, which takes the elliptic curve discrete logarithm problem from the curve, and via the Vey pairing moves it over to the multiplicative group of a finite field. And by doing that, in the supersingular case, since the embedding degree is potentially just 2, it means that the discrete logarithm problem was moved into a group which was kind of too small to be secure against known discrete log attacks in the basically index calculus type attacks in the multiplicative group of a finite field. But then on the positive side, there was like an overwhelming number of papers, literally thousands of papers written in the first decade of the 2000s on positive applications of the Vey pairing in cryptography, starting with Bonet-Franklin's identity-based encryption system and Zhu's tripartite three-way Diffie-Hellman And lots more applications such as short signatures, public key encryption with keyword search, and even partially homomorphic encryption. So with that, I hope I've convinced you that a lot of these techniques that Sayre introduced in his Harvard course in 1985 were, very foundational for, well, certainly for computational number theorists like myself, who went on to work in not just in coding theory, but also in cryptography. And you could see that reflected in both the construction of curves for use in cryptography, and also the use of the VE pairing to enable very, very interesting and powerful applications in cryptography. So with that, I'd like to just once again thank Jean-Pierre Sayre for his course, which I couldn't attend, but his notes and his collaboration, and all of his support over time. And for just a little bit of a shout out to all of the researchers and professors at the IML, the Institut de Mathématiques de Lumini, who supported this line of research. They were really a center for research on curves over finite fields for many decades, when it felt like many people in other parts of the world didn't care about it that much. So just in memory of Gilles Lachaud, and also Robert Roland, and François Baudier, and all my great colleagues from EML. So thank you very much for listening. We'll take more questions tomorrow, I think. Thank you.
Very much, Kristin. We'll move to questions. There is a question in the chat, although it's been answered, but maybe you want to weigh in on it. Why not larger genus?
Great, so glad you asked that. So what happened is that at some point, I forget the year, Adam and Huang published a sub-exponential attack on a billion variety, discrete logarithm problem for a billion varieties in larger genus. But larger really meant like quite a bit larger, like log Q large. And so like just take Q is 128 bits, then genus like 128. That's pretty big compared to 1, 2, or 3. So what about in between that, in between log Q and genus 2? Well, so what happened is there were some exponential time attacks that were published, but that were better than square root attacks. So there were the generic attacks on a discrete logarithm problem run in square root of the group size. And if I remember correctly, for genus 3, instead of 3 halves, like Q to the 3 halves, there was an attack by one attack by Deem, and maybe another attack by like Gaudry and others that was like 4/3, like Q to the 4/3 instead of Q to the 3 halves or something. I might have it attributed to the wrong person, but so there were several of these exponential attacks. And so once it was like considered that that it was better than generic attacks, it was somehow people got the idea like, oh, these are broken. But actually, in fact, they're not broken. So genus 3 is a really nice intermediate case. So what you can see in, I think the precise analysis is published in a paper that I wrote with Kim Leina on genus 3 attacks. So if you look at the Deem attack, and you put in all the log factors and the constant factors, it's actually worse than the generic attack. So for genus 3. So in my opinion, like when people say genus 3 is broken, I disagree. I do not think genus 3 is broken. That doesn't mean somebody won't come up with more attacks, or it could also mean somebody did something in the last couple of years that I don't know about. I'm really sorry if I missed something there, but anyway, and also, like I said, I can't remember the exact authors on the Gaudry paper, and the Klaus Deem's paper was a separate attack.
And there's a question from Christoph. Do you want to unmute and ask your question, Christoph?
Yeah, I mean, first, Kristin, thanks for trying to save Genius 3 for crypto. You're the first person trying to do it, so I'm glad if it could be helpful one day. Well, I think it might be helpful for this new trillionaire maps, like coming from the work of Wang when he tries, I mean, maybe even like Genius greater than 3. I just wanted to make a comment saying that indeed, you're right, saying that the connection between like curves with many points is less obvious with cryptos than with codes. But I think what you showed really well is that the tools that we are going to use in one case and the others, so, I mean, we import them from one place to the other. And right now, I think that somehow all the work which is done around graph of isogenies, this might be useful when you want to move inside certain isogeny classes in order to like go to the, I mean, to a Nabelian variety that is going to be a Jacobian. So yeah, I mean, these kind of pictures, I think we are going to see them more and more on the maximal curves side as well at some point. I mean, that's my hope at least.
Great. Yes, I totally agree. And that was really my larger point. So many of the tools that Sarah introduced and that people like myself were able to learn thanks to his notes were very valuable, like throughout my career. Like I said, like I've used the gluing techniques in, half a dozen different settings.
Yeah, and indeed, I mean, it goes in one direction, but also now, I mean, plenty of people need like these fast algorithms to count point to try, I mean, for a brute force attack to try many curves until we get one with many points. So, I mean, they are really complementary somehow all the time.
Absolutely. So I guess if there's more discussion or question in the Zulip, I'll try to check that before the talk tomorrow so that we can have more discussion. I'll continue with kind of lists of open problems and things, but if people want to ask more questions in the chat or tomorrow, that would be great.
Okay, great. I'll remind people that Kristin's second talk is the penultimate talk tomorrow in tomorrow's schedule. I don't see any other hands raised, so maybe we will end. Oh, Drew, would you like to unmute?
Yeah, actually, Kristin's answers to the last question encouraged me to ask this one. You mentioned twist security, but I've always felt like this was somewhat overrated. And I'm curious whether you know of any attacks, I mean, other than the obvious ones, I guess, of the systems that omit the Y coordinate. I mean, I've seen arguments that you shouldn't be relying on that anyway, and that if you implement it properly, there's no sort of clear twist attack that would take advantage of a twist insecure curve. Anyway, I'd welcome your thoughts on that.
Yeah, you're right, Drew. In fact, first of all, it's been a long time since I thought about that question. There is at least one or more papers published on the attacks that are known. But like you said, if you implement things properly with the proper checks, you won't be susceptible to those attacks. So that could be, at least my current memory and knowledge, that could be another way to avoid, issues with the twist. So you're right. I'm not sure that it's a really serious constraint. Constructing pairing-friendly curves is a very serious constraint. That is not something that can be achieved with picking curves randomly and counting points. But twist security, like you said, debatable.
Any more questions? Okay, let's thank Kristin again and join us again for tomorrow's talk.
Thanks, everyone. Bye.
Thank you.